In this video, we're going to discuss the importance and application of Kirchhoff's rules. So the first question is, why are Kirchhoff's rules important? So it turns out that there are ways in which resistors can be connected so that the circuits formed cannot be reduced to a single equivalent resistor using the series or parallel equivalence resistance formula discussed earlier. Just to recall, for resistors connected in series, the equivalent resistance will be R1 plus R2 plus R3, and for parallel, the equivalent resistance will be remember to take the reciprocal for the parallel combination. Now, when these two equations cannot resolve a circuit, then the only other option we have is Kirchhoff's rule. So the two rules outlined. The first rule is the junction rule, and it states that the sum of currents at any junction must equal 0. This is a statement of conservation of charge. You could also state this equation as sum of currents going in, so sum of currents going in equals sum of currents going out. This way, currents going in are treated as positive and current going out as negative. So more about the junction rule. If we look at these two diagrams, the amount of charge flowing into or flowing out of the branches must equal the amount flowing into a single branch. The analogy here is water flowing into a pipe that splits into two pipes. So the amount of water flowing out of the two branches must equal the amount coming into the main pipe, and both cases are the conservation of charge in the case of the current and conservation of mass in the case of the water. So in equation form, you would say I1 equals I2 plus I3. Alternatively, you could rewrite this equation as I1 minus I2 minus I3 equal to 0. And so we've used the convention that current going in is positive, current going out is negative, so as mentioned earlier, this equation or the first rule is required by the conservation of charge. So basically, charge cannot be created or destroyed. Now, the second of Kirchhoff's rules is called the loop rule. The loop rule states that the sum of potential differences across all elements around any closed circuit loop must equal 0. this is a statement of conservation of energy. So in equation form, this is the loop rule. Sum of delta V is the voltage, the potential difference around a closed loop must equal 0. And by Ohm's law, delta V equals I times R, and we're going to discuss the sign convention. So these are the two of Kirchhoff's rules. The junction rule, I in equals I out. That means I1 equals I2 plus I3. And then the second diagram, this diagram shows a circuit that has 4 elements. So these 4 elements could be resistors, they could be batteries, or any combination of the two. But the second rule requires that the sum of the potential differences across all the elements in one closed loop must equal to 0. So let's discuss the sign convention. We know that current, the direction of conventional current, that's the flow of positive charges, always goes from high potential to low potential. So as you traverse a resistor in the direction of the current, you're going from high potential to low potential, so the potential is actually dropping. So traveling around the loop in the direction A to B in figure A, the resistor is traversed in the direction of the current, and therefore the potential difference is minus I times R. So you're going from high, which is positive, to low, which is negative. Remember, the negative terminal is treated as 0 potential. So 0 minus I times R gives you negative IR. Now, in the second figure, if you traverse the loop in the direction opposite to the current, then the potential difference across the resistor will be plus I times R. So since the current is going from B to A, so B must be high and A must be low. So if we traverse the resistor going this way, as in the first case, we're going from low to high. So you're going from like 0 volts to I times R volts. So delta V is equal to IR minus 0, which is plus I times R. Now, a final note about the loop rule. So what happens if in traversing a loop you come across a battery or an EMF source? So the convention is the same. So if you go from A to B, as in figure C, you're going from low to high. Low is like 0 volt, and then high is the value of the battery. So going this way, the potential difference is E minus 0, which is plus E. Now in D, if you traverse the barrier again this way from A to B, now look at the orientation of the barrier. We're going from high to low. That is, we're going from E to 0. So the change in voltage is 0 minus E, which is minus E. So basically, when you traverse a barrier from high to low, the potential difference across the barrier is negative. So in this diagram, the loop is shown by the purple line. So if we traversed the circuit in this direction, then we're going across the barrier from low to high. Therefore we have a potential difference of plus E. And as we go across the resistor, notice that the conventional current goes in this direction. So and current flows from high to low. So therefore this side will be positive and this will be negative. So as we traverse in this direction, the potential difference across R is minus I times R. So to summarize, to solve a problem using Kirchhoff's rules, you're going to apply the junction rule as often as needed, as long as each time you write the equation, you include in it a current that has not been used in a previous junction rule. In general, the number of times the junction rule can be used is one fewer than the number of junction points in the circuit. If this sounds confusing, just ignore it. It will become clearer when you work out examples. The loop rule can be used as often as needed, so long as a new circuit element, resistor or barrier, or a new current appears in each new equation. And in order to solve a particular problem, the number of independent equations you need to obtain from the two rules must equal the number of unknown currents. So for instance, if you looking for 3 unknowns, then you need a minimum of 3 equations. If you're looking for 2 unknowns, you only need to write down 2 equations. Now take note, if there's a capacitor in any branch, then the branch becomes an open circuit. So the current in the branch containing a capacitor will be 0 under steady state conditions. This will become clearer in the next chapter. So here's the problem solving strategy. Study the circuit diagram and identify all the elements. Very important. Identify the polarity of each barrier. So identify the high and low terminals. Imagine the directions of the currents in each barrier, and then determine if the current, if the circuit could be reduced by combining series and parallel resistors. If so, then you can proceed using the equations for series or parallel. Now, if the circuit cannot be reduced using these two equations, then proceed by applying Kirchhoff's rules. Now, assign labels and symbols to all known and unknown quantities. Assign directions to the current. Take note the direction is arbitrary. So it's basically a guess, but you must adhere to the assigned directions when applying Kirchhoff's rules. Now, apply the junction rule to any junction in the circuit that provides new relationships among the currents. Apply the loop rules and choose a direction in which to traverse the loop. Now, you must correctly identify the potential difference as you cross the various elements. And then finally, solve the equations simultaneously for unknown quantities. Finally, check your numerical answers for consistency. And if any current value is negative, it simply means that your initial guess for the direction was wrong. It doesn't mean the answer is wrong. It just means the direction is opposite the assigned direction used in the equations. So the magnitude of your current will still be. So let's apply what we just learned in this circuit. So here we have two junctions, J1 and J2, and we want to write down the equations for Kirchhoff's junction rule. So at the junction level J1, the current going into the junction is I2, and the current going out is I1 and I3. Notice that I1 actually comes like this, and then I3 like this. That's how we know that I1 and I3 are out. So sum of currents in equals sum of current out. For the junction labeled J2, clearly I1 and I2, I1 and I3 are going in. So this is in, this is in, going into the junction J2, and then I2 is going out. So I2 is going out. So sum of currents in equals sum of currents out. And take note, we could write this as I2 minus I1 minus I3 equal to 0, and we could write this as I1 plus I3 minus I2 equal to 0. Notice that both equations are the same because of commutativity. So it doesn't matter which junction you use in this case because it yields the same two equations. So I2 equals I1 plus I3 is the same as saying I1 plus I3 equals I2. Now let's look at the loop rule. So for the circuit shown, write down the equations for Kirchhoff's loop rule for the loop labeled 1 and 2. You may want to pause this video, write down an attempt before watching the video for the correct response. So for loop number 1, the elements traversed in loop number 1 include, we have the 1 ohm resistor, we have the 2 volt battery, then we have the 2 ohm resistor, and then we have the 4 volt battery. So we have 4 elements traverse. That means we go across 4 elements as we travel in the direction of loop number 1, and loop number 1 is right here. This is loop number 2. So for loop number 2, the elements traversed include the 4 volts battery, the 2 ohms, the 1 ohm, 6 volt battery, and the 3 ohm resistor. So we have a total of 1, 2, 3, 4, 5 elements in loop number 2. Also note that loop number 1 and the loop number 2 are both clockwise. So application of Kirchhoff's loop rule to loop number 1, as we go across the 1 ohm resistor, the loop is going opposite the current. That means the loop is going from low to high. Take note, current flows from high to low. So if you go against the current, you're going from low to high. Therefore, the potential difference is plus I times R, which is in this case is plus I1 times 1 ohm. So plus I1 R1, but R1 is 1 ohm. Now as we traverse the 2 volt battery, we go from high to low. So we're going from 2 to 0. 0 minus 2 is minus 2. So minus E. And then as we traverse the 2 ohm resistor, we're going in the direction opposite the current. So plus I2 R2. And then as we traverse the last element, we go from low to high. So from 0 volts to 4 volts. And therefore the potential difference is plus E, which is 4. And then this equals 0. For loop number 2, starting from the 4 volt battery, the battery is traveling. Potential difference is 0 minus 4, which is minus 4 or minus E. And then we traverse the 2 ohm resistor in the same direction as the current. So we're going from high to low, which means the potential difference is minus I2 R2. And then again, as we go across the 1 ohm resistor, notice that the current through the 1 ohm resistor is the current labeled I3, because I3 comes from junction number 1 all the way around. So minus I3 times the 1 ohm. And then as we traverse the 6 volt battery, we're going from low to high, so plus E. And as we go across the 3 ohms, we're going in the same direction as the current, which is high to low, so minus I3 times 3 equal to 0. So that is how to apply Kirchhoff's two rules. In the next video, we're going to look at how to apply these two rules in actually solving a problem.